Assalamu alaikum wa rahmatullah. Our class of today is about transactions, which is chapter 4. As you remember, we have taken some topics before this. We started with introduction, then after that we started with the design, database design. So we learned about some concepts, basic concepts and so on. After that we learned how to make the entity relationship diagram. And after that, we learned how to transform the entity relationship diagram into relations. And after that, we learned the normalization, how to check or to validate our design through the normalization forms. We start with the normalization form 1, 2, 3, 4, and so on. Depends on the requirements. Then we learn about the query language. So we have the DDL, DML, DDL, and the control language. Okay. So after that, we talk about the data manipulation language. We have taken many examples and many scenarios, and also we gone through many practices. After that, now we stop with the transactions. Now we are going to start with it after the semester break. And after this, we have what they call it web-based database application, and also database programming, which includes the triggers, stored procedures, and so on. After that, we are going to learn about something called database application development using framework, which is all about MVC. Okay, so I'm trying to combine this number 7 with number 5 to start from the beginning with the MVC framework to make your life easier. And because the MVC is the latest approach that's very commonly used nowadays. Okay, that's why we want to learn it. We want to make it the default of our programming. Then here inside the web-based database applications, we are going to learn some Java server pages, and also we are going to learn some JavaScripts, also cascaded style sheets, what they call it, CSS, and what else we are going to learn about the MVC as an approach. Okay, so let us continue with the transactions first and see how this transactions works, and what's the functionality of that transactions, when we need them, when we need to make sure that we properly use them, and what type we have to use in each case. Okay. In this slide here, we have a very short introduction. So an application might face problems such as a power failure, hardware crash, some accidentally unplugs a cable, etc. So many cases could happen, right? So maybe network is disconnected, maybe the electricity cable is unplugged, or maybe the machine is crashed, or the power is has failure or something like that. So everything is possible, right? Or even internet could be disconnected, right? So in this case, if we are working on client server application, then in this case, the system or a transaction in the system, in our system, could be interrupted. So maybe during the moment of we are trying to save something into the server, then the internet is disconnected, or maybe the power is failed. In this case, what will happen to our transaction? We have to understand what will happen and how we can fix this issue, or take into account all of that issues. So such problems can be minimized. Always keep in mind the word minimized. because we cannot eliminate, 100% eliminate, but we can minimize. Okay? So it can be minimized by implementing backup and recovery procedure. This is one of the solutions, backup and recovery procedures. Then number 2, storing duplicate data to different drives. Number 3, installing uninterruptible power supplies, UPS. And nevertheless, failure at all at the wrong time can have serious consequences. So if let's say failure happen in the wrong time, which is the wrong time means the time that's very critical, that's during the saving of some data, or maybe during the running some process on your data or manipulating your data, then suddenly the electricity is interrupted, or maybe the internet is disconnected or whatever, then this is what they call it, failure at the wrong time. So that could make serious consequences. So it could corrupt our data. Okay? That's why it's very important to know about the transactions and how to take into account any possible failure. So issues of transaction failure here. A transaction is a set of changes that must all be made together. Okay? A transaction is a set of changes that must all be made together. Okay? So if let's say we want to, for example, if we want to create an order for a customer, for example, then the order information is going to be saved in a table, right? In the orders table. Then the order items will be saved in another table called order details, or maybe order items. Am I right? So in that case, if let's say we created the order header, then we created the order items, and after that we want to commit our changes to the database, and during the commit, for example, the order header is saved, and maybe we start to save the first order item, then the electricity is interrupted. So in this case, what we will have in our database, we will have a header of an order that has no items, and all the items will be gone, right? So in this case, this could cause a big issue, right? Especially if the system is critical. Maybe if this happened for the, for example, for the UBM system, for example. So you add some courses, or maybe the teacher adds some marks, then try to commit, then suddenly the electricity is gone, the marks is gone, and instead if you get you get, for example, 86 in a certain subject, you get only 0 or something like that, then the teacher doesn't know what happens, or maybe the exam is online, or they don't have a hard copy or something like that. It will be a big issue, right? So that's why it's very important to know how to deal with the transactions and how to take care about them. So transaction, the complete steps. For example, if let's say many things, like here, set of changes, for example, 2 or 3 changes that must be done together. So when we use transaction, these 3 things, this 3 or set of changes, either to be saved completely or not to be saved at all. So partially is not accepted. Partial save of the changes, it's not accepted. So the transaction will guarantee that either to completely save or save nothing or change nothing. Okay, this is the behavior of the transaction. For example, transaction for transferring money from saving account to a current account consists of two steps, right? So this is very serious case, right? Because this one is all about money. So if let's say we are developing a system like what they call it, Western Union or maybe MoneyGram or something like that. So that system supposed to give the or provide the service of money transfer. So if let's say a customer came to the counter and asked the employee to transfer 1,000, okay, 1,000 US dollar from his account to another account. So in this case, the employee will prepare the transaction that has two parts. The first part is to deduct the money from the source account, right? Then the money is supposed to be added to the target account, right? Sorry about that. So what will happen if the system deducted the money from the source account and before it saves it or added it to the destination account, the electricity is interrupted, or maybe the internet is disconnected, or maybe the hardware is failed or something like that. So in this case, the money is gone, right? The money is gone because money is deducted from the source account and not inserted into the other account. So here it will create a big issue for all parties, right? For the customer, for the person who is waiting for the money, and also for the employee and for the company itself. Okay. So that's why we have to start transaction. We subtract the money from the original account, then we add the money to the other account, and after that we end the transaction, so the transaction will commit everything if there is no failure. If there is any failure at the middle, then the transaction will be cancelled. So the money will be returned to the original account and everything will be taken back to the normal case before we start this transaction. Okay? What happens if the machine crashes after subtracting the money but before adding the money to current account? So this is the same issue that I just explained to you. So here in this slide, there is an illustration of transforming the money. So here we have the transaction at the left side has two steps. The first step is to subtract 1,000 from saving. This, for example, here at the middle, we have a machine crash. And after that, we add the 1,000 US dollar to checking, money disappears. Okay? So here, what will happen? Okay, Salmi, this one is 5340. I don't know why it's like that, but checking accounts and is like this. It's supposed to be, this is wrong, right? It's a wrong example, right? Anyway, so this is the original balance of the Salmi. So 5,340.92 cents. Then we deduct 1,000. So the account supposed to have 5340.94. So if let's say the machine crashes here, then we check Salmi's account. So it's supposed to get like this, right? But I don't know why they make it like that. As I mentioned, this is not my slides. Actually, this is the slides that comes from the computer science department. That's why we still have some mistakes, and every semester we correct some, then a new bugs appear. Anyway, so here, as I explained, the money could disappear if we did not use transactions. So here, transaction issues. How do we know that both operations are in the same transaction? So the first thing we have to know what parts or what changes are in the same transaction. So we have to find, for example, in the transfer of the money, so we have to understand, we should have the ability to understand that the deduction of the money from the original account and the addition of the money to the other account is or are both belongs to the same transaction. So either to successfully completely run or nothing should be changed. Okay, so we have these two choices. Okay, so based on this scenario, we should understand that the deduction and the addition of the money to the other account supposed to belongs to the same transaction, and the transaction should fail together or succeed together. Okay. The second thing, how does the computer know that both operation must be completed together? Okay, after we know the parts of the transaction, we should tell the computer where is the parts or where are the components of the transaction. So we have to do something in our code, right? To tell the computer and the compiler that these parts are supposed to be successful together or failed together. Okay. Then here, how do we tell the computer system which operations belongs to a transaction? Okay, let us go to the other slide. Here, business rule define what operations should be in a transaction. Actually, transactions are defined based on the business rule. So in order to understand the components of the transaction, you have to understand the business itself. So if you don't know how the transfer of the money works, in this case, you will never be able to understand what is the transaction. Okay, so at first you need to understand the business itself. Okay, then the application developer is responsible to tell the computer system which operation belong in a transaction. Okay. By marking the start and the end of the transaction in your code, so the computer will know where is the end, where is the beginning and the end of the transaction. When the computer sees the start marking, it first writes all the changes to a log file. So this is the steps that will be done when we deal with the transaction. So if let's say we have transaction, the computer find a transaction beginning, for example here, then it will start running everything and writing all changes to a log file. Okay, to keep track of all changes. So if let's say any failure happen at any point, then the log file should be used to recover the original data. Okay. When it reaches the end of the transaction, so if let's say the compiler reaches the endpoint of the transaction, then it makes the actual changes to the data in the corresponding table. So if everything is run smoothly, successfully, then everything will be committed to the database. So transaction either to run successfully together or fail together. This is the only two options when we deal with the transaction. But if we run some actions without transaction, so maybe one transaction will be partially successful and partially failed. Okay, so in that case, for example, the money transfer case, so maybe the deduction of the money is successful, but the addition of the money to the other account is failed. So in that case, the money will be gone and the system will be in an inconsistency situation. Okay, defining transaction, the computer needs to be told which changes must be grouped into a transaction. So turn on transaction processing, signifying the transaction start and signify the end. Then here we have success, which is to save all changes, or failure to cancel all changes. So must be set in module code, must be set in module code. So here we have Oracle and we have Microsoft Access. I don't know why all the time they compare with Microsoft Access, because Microsoft Access is not an actual database actually. It's a very simple database application that comes with the Office. That's why I feel like they are trying to show strength of the Oracle on the expense of another product. I don't care about the Microsoft Access actually. So here we have in the Oracle, we have start transaction. Then we have either to commit or to roll back. So we commit only if everything successfully run, and we roll back if there are partial failures. Okay, so this is how it works. Is there any question before I continue further?
No.
Okay, the concept is very simple, right? Okay, here in this slide we have an example by code. So here we have a function, create function, transfer money, amount, currency. This is one parameter, amount. The type is currency. The other parameter is account from. The type is number. The other parameter is account to. The type is number. Then the function will return a number. Okay, after the function finish, it will return a number. So it could return -2, it could return -1, it could return 0. Okay, so it depends on what we have done inside the function. Or maybe we can make this return Boolean. Okay, so in this case, if Boolean, it will return 0 or 1. So if, for example, 0, that means false, 1 means true, and so on. Okay, so that could reflect the case of the function. Is it failed or succeed? Okay. Here, what do we have here in this line? We have a private variable called current balance, CUR balance, and the type is currency. So you have to differentiate between the parameters. These parameters like amount, account from, account to, all of these are parameters that's passed from outside the function. So when we call the function, we give it values for these parameters. But the current balance here is a local variable that's going to be used inside the function only. It's not going to be passed from outside. Okay? So here, after that, we have begin and end of the transaction. So inside the begin and end, we started with declare handler for SQL exception. Sorry, guys. Okay, declare handler for SQL exception. Here we have begin and end. I think I have to turn off the AC. Okay, here we have rollback returns -2. So this one is a flag for completion error. Okay. So if the function ends with -2, that means the function is not successful. It runs with some errors. Okay. Then here after this is only to declare the handler for SQL exception. After that we have start transaction. Actually, after this, this is only comments. Okay, it's not going to be run. This one is only comments. Okay. This one as well. So here we start the transaction. So the computer knows that this code between the start transaction and the commit is part of the same transaction. Is a part of the same transaction. Okay. Here, the start of the what they call it, the transaction. They at the beginning they have to find the current balance, right? So they have to make a query of the current balance and save it into the variable. Save it into the variable. Okay. So the value of this query will be saved here. Then this variable later could be used. Okay. Here select current balance into CUR balance from accounts where account ID equals to account from. So this is the original account that we want to deduct money from. Because before we transfer the money, we need to make sure that the original account or the source account has enough money to complete this transaction, right? So that's why we have to make a query to retrieve the current balance. Okay, then here, after we save the current balance into the CUR balance variable, then we check the current balance here. Is it less than the amount or greater than the amount that we want to transfer? So if less than the amount, that means error, right? And the error should show that there are insufficient money. There are insufficient balance. Okay. That's why here we return -1. Okay. -1 or -5 or -10, it's up to you. You can design it anyway, as you want. Okay. It's not necessary to be -2 or -1 or 0. It's not necessary. It's up to you. You can play with it as you want. But after you make it, you have to document. You have to write documentation about it for the others, or maybe for your team members to understand about the function and how to deal with it. Yes, you have to tell them that if the function returns -1 for you, that means the balance is not enough from the original account. Okay, so you have to do some documentation. Then after that, after the if ends here, so this function actually, or this line is going to be executed only in the case of the current balance is less than the amount that's needed to be transferred. Otherwise, the execution will not enter inside. So if the balance is enough, If the balance is more than the amount, then the table of the accounts is going to be updated. So here we will update accounts, set current balance equal to current balance minus amount. Current balance is the table field. Okay, then current balance is equal to current balance minus the amount. So we deduct the amount from the original account, where the account ID is the account from. Okay, so here is to deduct the money from the original account. Then the second step or the third step is to add the money to the other account. So here we need to update the accounts, set the current balance for the other account equal to the current balance plus the amount, where the account ID is equal to the account 2. Okay, is that clear, guys? Is that clear or not?
Yes.
Yeah, it's very simple, right? So here, all of these 3 steps must be succeeded together or failed together. So we cannot save only this part, then suppose that failure happened here, we keep this changes applied. We cannot keep. If the failure happened here, then the transaction will roll back everything. Okay? Then after it roll back, it will return -2. Will return -2. So in this case, -2 means everything is not completed. Everything was not completed. Okay, and the system is returned back as normal. But if everything runs smoothly, successfully, then we reach the commit without any failure, then the transaction will save the changes to the database, and after that it will return 0. 0 means everything was successful. Okay, so maybe we make this 0, or this one -1, this one -2, or maybe this one is, for example, 1, this one is 2. It's up to you. You can design it as you want. It's not necessary to be -2 or minus. It's not necessary to be -2 or -1 or 0. Okay, it's up to you. Okay, this is the what they call it, the transaction. We still have something called save point. Save point. Save point actually is to save the system at a certain points. Okay, it's not like the transaction. It's not like the transaction. So if, let's say, we have a transaction that has many things to be run together, but some of them can succeed together, even if the others could fail. Okay? So in this case, this is what they call it, partial successful. In this case, if we want to use the save point, so maybe we need to partially run some of the steps of the transaction. Okay, so here the example is, as you can see here, this is the start point and this is the timeline. This is the timeline. So here we have something called required elements. Then, for example, we have a save point, which start optional. And then after that, we have some risky steps. If this steps has failed, then we could roll back to the save point. Okay, we can roll back until here, not until the beginning of the transaction. Okay? So in this case, if we roll back until here, then this part will be saved anyway, and that part could be not saved, right? So here we save partially some of the transaction. And as you can see here, we have the commit. So partial rollback could be done when we use the save point. Okay? So how it works, it could be written as you can see here in this slide. So here we have start transaction command, start transaction. Then after that, we could run select statement, we could run update statement, and whatever. Then after that, we could run this command to create a save point. So here, save point name is called start option. Okay. Then after that, we could run update or other update or delete or set or whatever. Then after that, we check if error, then roll back to the save point. So if we check some errors, maybe based on some queries, we found that there is an error, then in that case, we could roll back to the save point. So rolling back to the save point is based on this command, roll back to save point and the save point name. Then after that, we could commit or could continue with the transaction or do whatever. Okay? So from this point, we roll back to this point. That means all of these steps are cancelled, rolled back. Okay? But these steps are already executed and already saved. Especially if we went up to the commit without any failure, then this part will be committed. Okay? Is that clear, guys?
Yes, Doctor.
Yes,
Yes.
Doctor.
What if the before save point got error?
If here you got error here,
Yeah.
then the entire transaction will be rolled back.
Oh, okay.
Yeah. But if you got failure here or an error, not exactly failure, an error, this based on that error, certain error that you can check, not the error that's detected by the system automatically. If an error detected by the system automatically, then the entire transaction will be rolled back. So if let's say there's an interruption of the electricity happens here, then everything will be rolled back. But if let's say you did some operations here, you calculated some things here, then you found that your calculation is wrong, and because that's wrong, you should return everything back to normal, and you roll back to the save point. Okay? Let us take an example. Here, start transaction. Select star from employee. Update employee set salary equal to salary times 1.05. So here we increase the salary by 5%. Okay? So all employees got their salaries increased by 5%. Then update total set salary equal to whatever. Then after that we created a save point called start optional here. Then we insert into base lib values, select employee, blah, 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 salary times 1.05 and whatever. Then after that, we checked something, whatever we can check. Then we find that we have to roll back. So in that case, we need to roll back to the save point. So this step will be cancelled. Okay. Then after that, we start the we roll back to the save point. Then the end if is run here, and we come to the commit. So all of this will be saved, committed to the database, but this part is not going to be saved into the database. Okay. Later, we will take some examples on the real database. Okay. When we need to use transactions, actually transactions should be used when we have in stable situation, like electricity is not stable, or network is not stable, or whatever. And even to if we don't have instability in our system, we still have to use transactions because we want to guarantee all parts of any transaction have to success together or fail together. Okay? So our data will not be in inconsistency mode. Okay? Inconsistency mode means there is something wrong with the data. So as we cut the money from a certain account and we did not add them into another account. Okay. Another thing called concurrent access. Concurrent access is another concept. Actually, concurrent access means accessibility from multiple users at the same time. Accessibility of something from multiple users at the same time. So here, concurrent access, multiple users or processes changing the same data at the same time. So final data will be wrong. Okay? Force sequential, the solution is by forcing the operation to become sequential instead of concurrent. The sequentiality is guaranteed by using the locks or by delaying some batches. Okay, so either we delay one of the user or we lock the variables that someone wants to change. Okay, you will understand after we take the example, you will understand. Okay, two processes here. The first one receives payment 200, and the other one place new order for 150. Then initial balance was 800. Result should be 800 minus 200 plus 150. The final balance will become 750, right? But interference result in either 600 or 950. Okay? The result here, because causes the 600 or 950 of the balance because of the concurrency. So if let's say here, this is the balance, this is the customer table, and this is the balance. The balance was 800 at the beginning. So if let's say this one is the receive payment, and this one is the place new order. Okay? So here, if let's say this one is run first, if let's say this one run first, and then we run this, the result will become 750. So here, 800 minus 20, it will become 600. Then after that, 600 minus 150, it will become 750, or plus 150, sorry. 600 plus 150, it will become 750. But the case of concurrent accessibility here, if let's say two processes check the balance at the same time, so the first one here got the balance, current balance was 800, and the other guy here, or the other process, got the current balance as 800. Then this guy subtract 200, and this guy at the same time adds 150. So the result is depends on who saves after, who saves at last. So if this one saves the new balance after this operation finish, then the new balance will become 600. But if let's say this one finishes faster, then this one adds the amount, the 150 amount, then the new balance will become 950. Okay? Why? Because they access and read the current balance at the same time, then every one of them made different operation. Okay, so that's why concurrency is a not good thing to have. Okay, so we have to take care of the concurrency. We have to use locks. We have to use sometimes the delay and so on to avoid this kind of problems. Okay, problem is clear, guys?
Yes, yes.
Yes.
Anyone doesn't understand? Okay. If no questions, I'm going to go to the next slide. So here in the next slide, we have to, okay, here we see, if let's say we read the balance at the same time, this operation is performed first, then saved first, then what we have here is 800 plus 150, and at last 950 is going to be saved. And if this one is, if the right side operation is faster, then at the end we will have 600. Okay. What to do to avoid this issue is to make them sequential, to make all processes sequential. Not every process, but only the processes that needs to change the same thing, that needs to change the same data. Okay? So things that shares the same data or wants to change the same data have to work in serialization or sequential mode. So one by one, we prepare or finish, run the first operation, then after that, we run the second operation. Okay? So here, one answer to concurrent access is to prevent it. So we have to prevent the concurrent access. When a transaction needs to alter data, it places a serializable lock. So we have to use what they call it serializable lock. So when we lock the data, nobody could change it. Nobody even could read it. But this is depends on the type of the lock, because locks has two types. We have pessimistic looks and optimistic looks. So the pessimistic and the optimistic are a little bit different. Okay, one of them allows reading but doesn't allow changing. The other one doesn't allow anything. Okay, so here we have what they call it pessimistic looks. If you don't understand the meaning of pessimistic, you can translate it into Bahasa Melayu to understand it. So here, Kobe, because I can't explain to you what is the meaning of Bahasa Melayu, really. Oops, still pessimistic. Don't know why it doesn't copy. Okay. Is it correct? The other one is optimistic. Optimistic, I think. Optimistic, like this. Do you understand the meaning of this two?
Still not clear, but it's okay.
Still not clear.
Yeah.
Okay, the first one actually is the first one is that always assumes the worst thing. The first word, pessimistic, assumes the worst thing is going to happen. And this one assumes that, okay, everything is easy, we take it easy. So this guy here, the pessimistic look, doesn't allow reading and writing for any data. Okay, so even reading is not allowed. But for optimistic is another thing. So they may allow reading, but they don't allow writing, or they don't allow changing the data. Okay. So when a transaction needs to to alter data, it places a serializable look on the data used. So no other transactions can even read the data. So here, because this one is pessimistic, nobody even could read this data until the first transaction is complete. So this data, actually the balance is going to be blocked only for the use of the first transaction. So after the first transaction finish, then after that the lock will be released, so other process could read and write. Okay, so this is what happened. Other transactions no other transactions can even read the data until the first transaction is complete. So in this case, when we read the balance, so the balance will be locked by pessimistic lock. Then the other process will be waiting for the resources. Okay. Then after that, we finish here, we subtract the amount. So the new balance will become 600. After that, we release the balance. So the lock will be released. Then after that, the other process could be able to read the new balance, which is 600. Then it could add 150. So the new balance will become 750, which is correct. Okay. So as you can see here, the execution actually of this two process is like this. Okay, so we run this first, and after that we go to the other transaction. So if let's say we have another transaction here, then this one will run another lock, then after that it will be like that. So if you can see here is a serial, right? So one after another. Is that clear, guys, or not?
Yes, yes.
Okay. Okay, how to make pessimistic locks? Pessimistic locks actually is like this. Set transaction serializable read write. Read write means read and write are not allowed. So the look is pessimistic. Okay, so here if let's say we want to update the account, so here we started the look first, then we go and update the account, update the balance first, then after that, after we commit, the lock will be released. Okay, so in this case we lock the read and write. So here, as you can see here, read balance cannot, there is an error. Actually this error is not going to be bobbed up to the user or to the customer, because this error will be handled by the system itself, by the DBMS. So the DBMS will know that the second transaction need to be waiting. Okay, so that second transaction is going to be waiting until the first transaction is finished. Then after that, it could read the balance, and after that, update the balance by adding 150, and everything will be correct. Okay, so here in the transaction to transfer money here, we need to set transaction serialization read and write first, Then after that, we update the balance and we commit. Okay? Okay. The problem here is what they call it, deadlock. I think all of you knows about the deadlock, right? Guys,
Yes,
look,
doctor.
all of
Yes.
you knows about the deadlock. So do you have in mind the real example of the deadlock?
We know the term, but we did not know details about deadlock.
Okay. Okay, because the example here is not clear. That's why I'm going to go back to the money transfer example here. Yes, this one. So in this case, if let's say I'm going to copy this to make two cases that runs at the same time. Okay. But please pay attention here. This is very, very important. If you miss this part, you will never understand what is the meaning of the deadlock and how you have to avoid them. Because deadlock is very, is a killing error, actually. It's a killing error. If it could destroy your system, then it could involve you in a very big issue in the court, or maybe it costs you money to be paid for I mean, instead of the negative impact that you caused by your system and so on. So here, if let's say this function is to transfer money from account 100 to, okay, I will put account A100 to account B200. Okay? Then this right side is going to transfer money from account B200 to account A100. Okay? As we mentioned here, the systems or the big systems that has multiple users. So every user could run something, right? So suppose that this one is Western Union system. So the users of the system could be placed in different countries, right? So maybe I send money to my friend Ali in Libya, for example, at this moment, and at the same time, Ali, my friend Ali, wants to send me money at the same time. So in this case, if A100 is my account and my friend's account is B200, so if it happens at the same time that the two friends wants to transfer money to each other, and the system users wants to key in the transaction, and suppose that they run the the pessimistic look. If they run the pessimistic look, for example, so I will copy this. If they run the pessimistic here, so suppose that they run this here, and the other guy also run pessimistic look here. So here, let us see. Account from is what here? Is A100, right? And here, account from is what they call it, B200, right? So if let's say this guy looks the A100 and this guy looks the B200 at the same time. So this guy actually, when he tried to look the other account, he will find it looked by another process. So it will be waiting, okay? And this guy trying to look up this one, find it looked by another process. So this guy also will be waiting. So this guy at the left side will be waiting for the guy on the right side, and the guy on the right side will be waiting for the guy on the left side. So each of them will be waiting for the other. Endlessly. In this, how they can say it? Endlessly. So infinitively. Forever they will wait for each other. Okay? So the system here will be locked. And this lock is called deadlock. Deadlock. Why? Because the system is already dead. It's not going to be released anywhere. Okay? Do you understand it?
Yes, yes.
Is that clear or not? If not clear, I can explain in different way.
Can.
Huh?
Can.
Yeah.
Clear. Okay. Good. So if it's clear, then we should move to I don't know why this one is like that. We should move to the other topic here. So the deadlock here could happen when two or more processes have placed locks and locks on data and are waiting for the other's data. So for our example, the person number one looks the data for the account A100 and waits for the data of the account B100. And the other guy looks the B100 and waits for the A100. So that's why both of them will be waiting for each other forever. The solution actually is by applying something called random wait time. So the system, the DBMS, will apply something called random wait time. So it will guarantee that operations will not happen together at the same time. So in the previous case of transferring money, the person on the left side will look the two accounts A100 and B100 at the same time. Then it could finish before the other guy looks anything. Okay, that's why random wait time is a very good thing to be applied. Also, they have something called Global Lock Manager. So the Global Lock Manager here is a centralized process or application or function that's able to see the entire system and could find or realize when the deadlock happens. So if the system realizes that there is what they call it a deadlock, then it will release some of that locks. For example, it will release this lock, then the account B100 will be released. So the first person will be able to finish the transfer of the money. Then the other guy could repeat the operation until it success. Okay. The other one is to apply something called two-phase commit mechanism. Two-phase commit mechanism. Let us go and see, because later we are going to take some solutions, some examples for the solutions. Let us see the deadlock here. It's already explained. Actually here, the guy looked at the data A, which is the account, the first account, then tried to look the second account, and unfortunately it's looked by another person, so it will be waiting for the other account, and that the second process looks the first account and waits for the second account to be looked, but unfortunately that first account is looked by another process, so both of them will be waiting for each other forever. Okay, this is what they call it, the deadlock. So here, deadlock transaction 1 time A, B, C, then transaction 2. Here is an example if you want to go through. So if let's say update employee, set salary equal to salary times 1.1, where employee number equals to 100. So here transaction 2 wants to set or update the manager ID for the employee number 2000, sorry. So this guy actually will look the employee number 2000, and this guy will look the employee number 1000. So when this transaction wants to do something for the 2000, employee 2000, it will try to look it, but it's already looked by transaction 2. So here it's going to be waiting, right? Waiting for the transaction 2 to finish. And transaction 2 cannot finish until it look the employee 1000. And employee 1000 is already looked by transaction number 1. So this one is also going to be waiting for transaction 1 until it finish. So this one cannot finish, this one cannot finish. They will wait for each other forever. But the system could interrupt, so it could delete the 2 looks or interrupt the 2 transactions, and it could return an error message called deadlock detected while waiting for resources. Okay. Here, the solution. Solution number 1 is to apply what they call it random wait time. So when a process receives a message that is must wait for a resource, the process wait for a random length of time. Then it will try again. So it also need to release all existing locks, rollback statement, and start over if cannot obtain the resource. So what will happen here, if let's say this one looks 1000 and this guy looks the employee number 2000, and the execution came to this point here, and this transaction wants to look the employee number 2000, and 2000 is already looked by another transaction, so the system will apply random waiting. For example, it will wait for 30 seconds. So if 30 seconds the resource is not getting from the other transaction, if not released from by the other transaction, then this transaction will be rolled back, and everything, all looks will be released, even this one. So the look for the employee number 1000 will be released, so that guy could finish. Then after that, it will release the 2000 and 1000. Then the other transaction here could continue. It will find the 1000 and the 2000 released. Then after that, it could execute smoothly and everything will be successful. Okay, so this is what they call it random wait time. So we apply random length of time for every process that cannot get the resources. So if the process cannot get the resources, it will wait for a random length of time. If that time expires, then the process or the transaction have to release all existing looks to allow others finish. Then after that, it will start over until it obtain the resources. So this one is easy to program, but it causes a lot of time waiting, particularly when there are many active processes. So this one is easy to program, but causes a lot of delay. Okay? A lot of unnecessary delay. So here, solution number 2, what they call it, global look manager. So the global look manager here, a look manager monitors every look and wait. So every look created by a transaction will be monitored by this manager. So if the look manager detects a potential deadlock, it will tell some of the process to release their locks, allow other process to proceed, and then restart the other process. Okay? So for example, if let's say here, if let's say this guy looks the 1000 and this guy looks the 2000, then the deadlock manager will see that there are deadlock here. So this guy is waiting for this, which is locked by transaction 2, and this guy, transaction 2, is waiting for the employee number 1000 that's locked by transaction number 1. So the deadlock manager will decide which one is need to be released. So if let's say it decides to release the transaction number 2, so that employee 2000 will be released, then the transaction number 1 could be able to finish, and after it finished, the transaction number 2 should start over and should be able to get the 2000 and the 1000 and finish the process. Okay? So the look manager looks like this. It will have a table of resources and processes. So here, as you can see, actually I'm not going to explain this, because this one is only to show you how it looks like, but this is not a fully realistic table. So here, if this one resource B is locked, then we have locked and waiting for resource number D. Then we have to find another process that could be executed. So this one is locked here by the process number 2. So there is a clash here between process number 1 and process number 2. So process number 1 waiting for the resource D, which is locked by process number 2. And also process number 2 is waiting for resource number A that's locked by process number 4, and so on. So which one that needs to be released first to allow others to complete? This is the decision that will be made by the deadlock manager. Okay. Solution 3 is what they call it two-phase commit. Two-phase commit. So in this case, the DBMS handles concurrent access and deadlock resolution automatically, when write code to change data, the DBMS still tries to handle the situation automatically. However, the DBMS may rely on the developer to back out your transaction. Some systems may simply generate an error when the second process attempts to access the data, and it's the developer responsibility to catch the error and handle the problem. So this is all about the what they call it, the two-phase commit, which is the responsibility of the developer to make it. Okay, so there are only these 3 solutions, so we have to select which one. So these solutions actually to avoid the deadlock that happens by the by the pessimistic lock, by the pessimistic lock. Okay, let us go to see the optimistic lock. Optimistic lock is that supposes things are easy, no need to look the read and write and everything. We can make the things easy, and we take it easy. We don't expect that the concurrency will happen. So pessimistic looks and handling deadlocks was relatively standard in many systems for several years. However, as computer system performance increased, DBMS can process transaction faster and resulting in a lower probability of concurrency problems. A new approach seems to gain favor, which is the optimistic looks. Optimistic looks assumes that collusions are rare and unlikely to arise. Okay, so that's why they call it optimistic. Here, optimistic looks allow all code to read any data, no lock. So when we read, we don't lock anything. But when code tries to write a new value, so when we try to write a new value for a certain data, we have to check. So check to see if the existing value is different from the one you were given earlier. If it's different, someone changed the database before you finished. So we read, if let's say we read the balance, we found it 800. Then we did some calculation, and after that we want to save. Before we save, we try to read again. So the first read was 800. When we read the second time before we save, we found it 600. That means somebody else have changed the data, right? So in this case, we have to react based on the changes. Okay, so we have to take the changes into account. So maybe if somebody else changed it, then we need to cancel everything. So it depends on the business. Or maybe if somebody else changes, we need to take the new balance into account. Okay? But if let's say we read the first balance, we found it 800, then after that we did the process, and after we finish the process, we want to save, we read the balance again, we found it 800, still 800, then we save easily. Okay, no need to be suspicious about anything. So here, if it's different, that means someone changed the database before you finish it, so it's a collusion, raise an error. So maybe if the balance is changed, we need to raise an error. So reread the value and try again. Okay, maybe we need to reread the value and try the process again. Here, it can improve performance, but it requires us to deal with the collusion. Okay, this one is very good way, but we need to deal with the collusion manually. So it's the responsibility of the system developer. Optimistic looks for simple update. So here, if let's say read the balance, add the new order value, write the new balance, check for error. If there are errors, go back to step number 1 and repeat everything again. This is how it works. Okay? Actually, it's not the only way to deal with the optimistic looks, but this is one of the very common ways to use it. Okay? So maybe you need to go back to step number 1 to repeat everything from scratch, or maybe to take into account the new balance only, whatever. It's your responsibility actually to solve this issue. Okay? Here is an example on the same thing. Here we have account ID. This one is receive payment, account ID number, amount, currency. returns number, then old amount currency. So here, test end boolean false. It seems that this one now, this function is going to return either false or true. Okay, so test end is the variable that's going to be changed, the variable that's going to be changed in the case of successful or failure. Okay, then here do until test end equal to true. So here begin, select amount into old amount where account number is equal to the account ID that's given as a parameter. So we find the amount, we save it into the old amount variable here. Then after that, we update the accounts. We set the account balance equal to account balance minus amount, where the account number is equal to account ID and amount is equal to old amount. Okay, you see here, this is the amount that we read from the beginning, right? To find the old amount. So here, if the amount that we saved here into the old amount is equal to the current amount that's retrieved from the table, that means we can save. Otherwise, this will fail, will not save anything. This will not run any update. So 0 rows will be affected if the balance is or the amount is changed by somebody else. So in that case, if SQL code equal to 0, that means 0 rows affected and number of rows is greater than 0, then here test end is equal to true. If let's say we updated one record, so the number of rows will be 1, right? So in this case, this number is going to be, this condition is going to be satisfied. So the test end will be true. So if this one is true, this will finish and it's not going to be repeated. Why? Because this one is already changed to true. So the until here, do until this become true. Now it becomes true, so everything will be finished. But if let's say if the amount is changed by somebody else, the number of rows will be 0, so this condition is not going to be satisfied. So this test end still false, is not going to be changed to true. Okay, that's why the system will repeat the process again. Repeat the process again and again until it successfully update the system. Okay, is that clear, guys? Is that clear?
Yes, yes.
So in this case here, in the previous case for the pessimistic look here, we have something called set transaction serializable read and write. But in our case here, in the optimistic, we don't have that such look. But the look here is formed by using this condition. So we have to confirm that the amount that we read at the beginning is still the same as we have in our table. If it's still the same, then everything will be committed. Otherwise, no changes will be committed. And the system will repeat and repeat until it succeeds. Okay? So here, optimistic look versus pessimistic look. Optimistic look assumes the majority of database operations do not conflict. Process each transaction in 3 phases: read, validate, and write. Read, validate, and write. So the first thing is read, then after that is update, but if the data is validated. So before we update, we put in the condition, we validate that the current value is as we read at the beginning. If it's validated, then we can write. Otherwise, we cancel and repeat. Okay? The pessimistic is assumes that the conflicts are most likely will happen. So that's why they look everything, read and write, and after that they process, they run the everything, they change, modify, and manipulate everything. Then after that they save. After they save, they unlock. So others can access data and do whatever. So this, the second one, the pessimistic, is more restriction, but no repetition of the steps. Okay, there is no repetition. It's more restriction, but has more restriction, but no repetition. The first one has no restrictions or less restrictions, but it could have many repetitions. So it's a trade-off between the security, what they call it, the you have to handle the situation actually. If for example you have many users who access the system at the same time, then it will be most likely to have concurrent accessibility. So in that case, maybe you need to apply pessimistic lock. Otherwise, you can apply optimistic lock, but you have to consider the repetition that will happen, which will delay your operations and so on. Okay, it's a trade-off. So we can compromise, for example, the delay to guarantee that our data is always in consistency mode. Okay, so here, as you can see the diagram, the duration of the pessimistic and the optimistic. The duration here is before the read. We look, retrieve, and look the row, modify, then commit. After that, we release. So the look is from the beginning until the end. But here, in the optimistic strategy, we retrieve the row. We retrieve the row. So still unlocked. After that, we modify the row. If unchanged, return error otherwise. So if the previous row is unchanged, how we guarantee that it's unchanged? We have to validate. We have to validate the values that we have read before. So the values, when we read them at the beginning, we save them in a local variable for validation purpose. After that, when we run, we run the update statement. We run and we check the value saved in our variable. Is it equal to the current value or not? If it's equal, that means nobody changed it. Then we modify and save without any problems. Otherwise, we may return an error or maybe repeat the process or whatever. So the look here, look life is starting from this point until this point. So it starts at the update, not at the read. Okay? So that's why the lifetime of the optimistic look is shorter than the lifetime of the pessimistic look. Okay? Here we have another concept called ACID transactions. So A stands for atomicity, C stands for consistency, I stands for isolation, D stands for durability. So atomicity is all changes succeed or fail together. Okay, as I explained from the beginning. So all transaction components must succeed or fail together. Consistency, all data remain internally consistent when committed and can be validated by application-defined checks. So consistency here, if we go back to the money transfer, if let's say we transfer the money, we deduct the money from the first account, and then we cannot save the money to the other account because of a failure, because of some failure happened to the system. So in this case, the money is lost, right? The money is lost between the two accounts. So it's deducted from the first account, but not added yet to the other account, and it's lost. This is what they call it inconsistency. So the data cannot confirm the real situation, or the data in our database is not reflecting the real situation. Okay? Isolation is the system gives each transaction the perception that it's running in isolation. There are no concurrent access issues. So here we have to guarantee that there are no concurrent access issues. So if concurrency is available, we have to apply some locks or maybe some random weight policies and so on. The other thing or the last thing is what they call it durability. Durability, when a transaction is committed, all changes are permanently saved even if there is a hardware or system failure. Okay, that's all about the transactions. If you have any questions, please let me know. I know that we theoretically explained this part, but inshallah, I will give you some examples using the real database, and not today. Inshallah, tomorrow we will try to take some practices. We will try to play with these transactions and see how they are affecting the performance of our queries. Okay? Is there any question? Guys, if there is any question, let me know. Otherwise, we are done. And we need to close this class to prepare for the tomorrow's class. Any question, guys?
I guess no for now.
Hopefully, inshallah. Okay, so let me return this back to normal. Okay.